When German tank commanders first encountered Allied armor repaired using what they dismissively called the Canadian cheap welding trick in the winter of 1943, their initial response was contemptuous laughter mixed with professional disdain for what appeared to be desperate improvisation by forces lacking proper engineering capabilities. Wehrmacht technical officers analyzing damaged Allied tanks captured during the Italian campaign filed reports describing crude welding repairs that violated every principle of proper metallurgical practice taught in German engineering schools. One Panzer Battalion commander wrote in his after-action report that the Allies were so desperate for operational tanks that they were literally welding them back together in field workshops using techniques that any properly trained German welder would recognize as guaranteed to fail under combat stress. The welds looked rough and unfinished, applied with what appeared to be improper rod selection and inadequate penetration, suggesting that Allied maintenance crews were either incompetent or working with such inferior equipment that proper repairs were impossible. Within 6 months, those same German officers would be filing increasingly desperate reports about Allied tanks that refused to die, vehicles that absorbed hits that should have been catastrophic yet remained operational, armor that seemed to actually become stronger rather than weaker after sustaining damage and repair. The story of Canadian welding innovation during World War II represents one of the most overlooked yet strategically significant technical achievements of the conflict, a metallurgical breakthrough that emerged not from university laboratories or government research facilities, but from the practical problem-solving of welders and mechanics working in freezing field conditions with limited equipment and urgent operational demands. This innovation would fundamentally alter the calculus of armored warfare by dramatically extending the operational lifespan of Allied tanks and enabling damaged vehicles to return to combat far faster than German planning had anticipated. The technique that German engineers mocked as cheap and improvised was actually a sophisticated approach to armor repair that took advantage of metallurgical properties that conventional welding practice ignored or actively avoided. By 1944, the cumulative impact of this seemingly simple welding technique had shifted the balance of armored warfare in ways that German commanders struggled to counter, as Allied tank formations maintained numerical superiority not just through superior production, but through unprecedented rates of battle damage repair and return to service. The Canadian contribution to Allied armored warfare capabilities began in the most unlikely circumstances imaginable, with a small group of welders and mechanics attached to Canadian armored units in Britain during the long period of training and preparation before D-Day. These men came largely from industrial backgrounds in Canadian mining, shipbuilding, and construction industries where welding was a common skill but formal metallurgical education was rare. What they possessed instead of academic credentials was practical experience with welding under difficult conditions, working with diverse metals and alloys, and solving problems through experimentation rather than consulting engineering manuals. When Canadian armored units began intensive training exercises that resulted in significant wear and damage to tanks, these maintenance crews faced the challenge of keeping vehicles operational despite limited spare parts and the constant pressure to maintain readiness for the eventual invasion of Europe. The solutions they developed through trial and error would eventually revolutionize how Allied forces approached armor repair and maintenance. The fundamental problem facing tank maintenance crews throughout the war was that armor plate welding required extremely high temperatures and specialized equipment that was rarely available in field conditions. And even when proper welding could be accomplished, the heat-affected zones around welds often became brittle and vulnerable to cracking under the stress of combat operations. German engineering doctrine held that damaged armor should be replaced entirely rather than repaired through welding, as the metallurgical changes induced by welding compromised the armor's protective properties. This approach made sense from a pure engineering standpoint, but created enormous logistical challenges, as damaged tanks had to be withdrawn from frontline service, transported to rear area depots equipped with proper facilities, stripped down to allow armor plate replacement, and then reassembled before they could return to combat. The time required for this process often stretched to weeks or months, effectively removing damaged vehicles from operational availability for extended periods. Allied forces facing numerically superior German armor in the early war years could not afford such extended repair timelines, creating desperate need for faster methods of returning damaged tanks to service. Canadian welders working in field maintenance units began experimenting with unconventional approaches that violated established welding practices but produced results that seemed to work despite theoretical problems. Rather than attempting to achieve deep penetration welds that fused armor plates completely, they developed techniques using multiple shallow passes that built up weld material gradually while allowing the metal to cool between passes. This approach reduced the heat input to the surrounding armor plate and minimized the size of heat-affected zones where brittleness might develop. The welds looked crude and unfinished compared to textbook examples, with visible ripples and irregular bead patterns that would have earned failing grades in any welding certification test. But when these repaired tanks returned to training exercises, the welds held under conditions that should have caused failure, and in some cases, the repaired areas seemed to perform better than the original armor. Word of these successful repairs began spreading through Canadian armored units, and maintenance crews started sharing techniques and modifications that improved results. By early 1943, Canadian field maintenance capabilities had advanced to the point where battle-damaged tanks could be returned to operational status in days rather than weeks, a capability that would prove decisive when Canadian armored units finally entered combat. The first combat test of Canadian welding techniques came during the Italian campaign in the summer and fall of 1943, when Canadian tank units faced German armor in terrain that favored defensive operations and produced high rates of vehicle damage from both enemy fire and the brutal conditions of mountain warfare. Canadian Sherman tanks participating in the advance up the Italian peninsula routinely sustained damage from German anti-tank guns, mines, and the hazards of operating heavy vehicles on narrow mountain roads where mechanical failures and accidents were constant threats. The standard Allied procedure would have required withdrawing damaged vehicles to rear area depots for repair or replacement of damaged components, but Canadian maintenance units instead brought their field welding capabilities forward, establishing repair facilities as close to the front lines as safety permitted. German intelligence officers monitoring Allied tank deployments began noting something unusual. Canadian armored units were maintaining higher operational readiness rates than comparable British or American formations despite similar or higher rates of battle damage. The key to this remarkable maintenance performance was the welding technique that Canadian crews had refined through months of experimentation and practical application. When a Sherman tank returned from combat with damaged armor plate, Canadian welders assessed whether the damage was suitable for field repair rather than automatically routing the vehicle to depot-level maintenance. Penetrations and cracks that would normally require armor plate replacement could often be repaired using the multi-pass welding technique, building up material to restore structural integrity and protective capability. The process was not quick, typically requiring several hours of work, as welders applied thin layers of weld material and allowed cooling between passes, but it could be completed in field conditions using portable welding equipment and without the specialized facilities required for plate replacement. More importantly, tanks repaired using these techniques proved remarkably durable in subsequent combat, with repaired areas often outlasting adjacent original armor plate. German technical intelligence became increasingly interested in captured Canadian tanks as the Italian campaign progressed, conducting detailed examinations of damaged vehicles to understand how Allied maintenance capabilities had apparently improved so dramatically. Wehrmacht engineers examining welded repairs on captured Canadian Shermans initially dismissed the work as crude and likely to fail under sustained combat stress. The welding technique violated German standards in almost every respect. The weld beads were irregular and showed signs of multiple passes where German practice would have used fewer higher heat applications. The heat-affected zones were broader than optimal, suggesting poor thermal control, and the overall appearance suggested work performed by inadequately trained personnel using inferior equipment. German metallurgists predicted that these repairs would fail catastrophically when subjected to the shock of armor-piercing rounds or the stress of sustained operations. These predictions proved spectacularly wrong as the campaign continued, and German forces found themselves fighting Canadian tanks that had obviously sustained and been repaired from previous damage, yet remained fully combat effective. The mystery of why the Canadian welding technique worked so well despite violating conventional practice would not be fully understood until post-war metallurgical analysis revealed the sophisticated principles underlying what appeared to be crude improvisation. The multiple thin-pass approach that Canadian welders had developed through trial and error was actually inducing beneficial metallurgical changes in the armor plate through a process similar to controlled tempering. Each pass added material while heating the surrounding metal to temperatures that relieved internal stresses without reaching levels that would cause grain growth and brittleness. The cooling periods between passes allowed the metal to undergo phase transformations that actually improved toughness in the heat-affected zones. The irregular appearance that German engineers had interpreted as poor craftsmanship was actually evidence of careful thermal management, with welders adjusting their technique based on visual assessment of heat color and metal flow rather than following rigid procedures. The result was repairs that were metallurgically superior to the original armor plate in some respects, creating reinforced zones that could absorb subsequent impacts better than undamaged areas. By the winter of 1943, Canadian field maintenance units were achieving repair rates that Allied logistics planners had considered impossible, returning damaged tanks to operational status in 72 hours or less in many cases, where conventional repair procedures would have required weeks. This capability translated directly into combat power, as Canadian armored units maintained higher percentages of their authorized tank strength in operational condition compared to other Allied formations. The cumulative advantage was substantial. A Canadian armored regiment might field 30 operational tanks, where a comparable British or American unit with similar battle damage rates could only field 25 due to vehicles awaiting repair. German commanders facing Canadian armor began noting in tactical assessments that Canadian tank units seemed to regenerate combat power far faster than attrition rates should allow, maintaining offensive pressure, even after engagements that should have significantly degraded their capabilities. The cheap welding trick was proving to be a force multiplier that German planning had not anticipated and could not easily counter. The full impact of Canadian welding innovation became devastatingly apparent during the Northwest Europe campaign, following D-Day, when the scale and intensity of armored operations created unprecedented demands on maintenance systems and tested the sustainability of Allied tank forces against German armored reserves. Canadian armored units landing in Normandy in June 1944 brought with them the field maintenance capabilities and welding techniques that had been refined through the Italian campaign, establishing forward repair facilities that could handle battle damage repair within kilometers of the front lines. The brutal fighting in the Norman Bocage country and subsequent breakout operations produced casualty rates among Allied tanks that threatened to outstrip replacement capacity, with individual tank units sometimes losing 50% or more of their vehicles in single engagements. Under these conditions, the ability to rapidly repair and return damaged tanks to service became critical to maintaining offensive momentum. The German response to the Normandy invasion had relied heavily on armored counterattacks designed to destroy Allied tank formations and prevent breakout from the beachhead, but these operations consistently produced results that puzzled German commanders as Canadian and other Allied tank units recovered from damage far faster than German intelligence had predicted. Panzer divisions that inflicted heavy losses on Canadian armored formations in one engagement would find themselves facing the same units at near full strength days later, a pattern that seemed impossible given the scale of damage observed. German after-action reports began documenting specific instances where individual Allied tanks, identified by tactical markings and battle damage in previous engagements, reappeared in subsequent fights, bearing evidence of field repairs, yet remaining fully combat capable. The realization that Allied maintenance capabilities far exceeded German estimates forced revisions to tactical planning, as strategies based on attrition of Allied armor through sustained engagement proved ineffective when damaged vehicles returned to combat faster than German forces could be reinforced. The welding technique that enabled these remarkable maintenance achievements had by this point evolved well beyond the initial improvised approaches developed in Britain and Italy. Canadian maintenance personnel had refined the multi-pass procedure through extensive combat experience, developing standardized approaches for different types of damage and training new welders in techniques that could be taught quickly but produced consistent results. The key innovation was recognizing that armor repair did not need to restore original metallurgical properties precisely, but rather needed to provide adequate protection and structural integrity using materials and processes available in armor repair field conditions. A welded repair that provided 70% of original armor protection, but could be completed in hours, was far more valuable than a perfect repair requiring weeks, and in practice, the Canadian technique often delivered 80 to 90% effectiveness through the beneficial metallurgical effects that German engineers had failed to anticipate. The climax of Canadian welding innovation's impact came during the battles to close the Falaise Gap in August 1944, when Canadian armored forces played crucial roles in encircling and destroying German forces retreating from Normandy. The sustained high-intensity operations during this period produced damage rates that would have crippled conventional maintenance systems, with Canadian tank units reporting vehicles damaged multiple times within days and requiring repeated repairs to remain operational. Yet Canadian maintenance crews working literally under fire in some cases managed to keep sufficient tanks operational to maintain combat effectiveness throughout the critical phases of the encirclement. German forces trapped in the Falaise pocket faced Canadian armor that seemed inexhaustible, with damaged tanks disappearing from the front lines only to reappear hours or days later, bearing visible evidence of field repairs, yet still fully capable of combat operations. The psychological impact on German troops was severe, as the apparent indestructibility of Allied armor contributed to the sense that continued resistance was futile. German technical intelligence finally began to understand the significance of Canadian welding techniques when Wehrmacht engineers conducted detailed examinations of battlefield wreckage and captured equipment in the aftermath of the Falaise battle. Analysis of destroyed and abandoned Allied tanks revealed repair work that had been performed multiple times on the same vehicles, with some Shermans bearing evidence of 3 or 4 separate armor repairs, yet having remained in combat service until finally disabled. The metallurgical examination of these repairs revealed the sophisticated thermal management and metallurgical principles underlying the Canadian approach, forcing German engineers to acknowledge that what they had dismissed as crude improvisation was actually an innovative solution to armor repair that produced results superior to German methods in field conditions. This realization came far too late to allow Germany to implement similar techniques, as the collapse of German industrial capacity and the shortage of skilled personnel meant that innovative maintenance approaches could not be widely adopted even when their value was recognized. The cheap welding trick had helped win the armored warfare campaign through a combination of technical innovation and the practical expertise of Canadian maintenance personnel. The strategic implications of Canadian welding innovation extended far beyond the immediate tactical advantages of maintaining higher operational readiness rates in armored units. Allied logistical planning for sustained operations in Europe had assumed tank loss and damage rates based on early war experience, with replacement vehicle production and shipping capacity allocated to compensate for anticipated attrition. The dramatically improved repair and return to service rates achieved through Canadian welding techniques meant that fewer replacement tanks were needed than planners had projected, freeing shipping capacity for other critical supplies and enabling Allied forces to maintain larger armored formations than German intelligence had calculated was sustainable. This logistical advantage compounded over time, as each tank kept in service through effective repair represented one less replacement vehicle that needed to be manufactured, shipped across the Atlantic, and transported to frontline units. German armored forces facing this sustained Allied tank presence found themselves in an increasingly untenable position as the campaign progressed through late 1944 and into 1945. Wehrmacht panzer divisions had relied on superior tank design and crew training to offset Allied numerical advantages, but the combination of overwhelming Allied production and Canadian pioneered repair techniques created a numerical disparity that German tactical excellence could not overcome. German tanks were generally superior to Allied Shermans in armor protection and firepower, but this advantage meant little when German forces faced 3 or 4 Allied tanks for every panzer they could field. The rapid repair capabilities that kept Allied tank strength high made it impossible for German forces to achieve the favorable loss ratios needed to offset Allied material superiority, creating a death spiral where German armored units were ground down through sustained attrition they could not match. The human dimension of Canadian welding's success reflected the practical problem-solving culture that characterized Canadian military contributions throughout the war. The welders and maintenance personnel who developed and refined these techniques were largely working-class men whose formal education was limited, but whose practical experience with metals and machinery enabled sophisticated innovation through experimentation and observation. These men worked under brutal conditions in all weather, often within range of enemy fire, performing repairs that required sustained concentration and skill despite cold, fatigue, and the constant pressure of operational demands. Their contribution to Allied victory was as significant as that of tank crews who fought the battles. Yet their work received little recognition or public attention compared to more dramatic combat actions. The cheap welding trick succeeded because skilled craftsmen applied intelligence and creativity to solve practical problems, developing solutions that academic engineers had dismissed as impossible or inadvisable. The post-war recognition of Canadian welding innovation came slowly and incompletely, as military historians and technical analysts began documenting the factors that had contributed to Allied victory in the armored warfare campaign. Detailed studies of tank operational readiness rates revealed the dramatic differences between Canadian-maintained units and comparable formations using conventional repair procedures, with Canadian units consistently showing higher percentages of authorized strength in operational condition, despite similar or higher combat exposure. Metallurgical analysis of preserved tanks bearing wartime repairs demonstrated the sophisticated principles underlying the Canadian approach, validating through science what welders had discovered through practice. Former Wehrmacht officers interviewed about their wartime experiences consistently identified Allied tank numerical superiority as a critical factor in German defeat, but few recognized that much of this superiority came not from production advantages alone, but from maintenance innovations that kept damaged vehicles in service. The legacy of Canadian welding techniques influenced post-war military maintenance doctrine and contributed to broader recognition that field repair capabilities could be as strategically important as production capacity in sustained military operations. Modern armies studying the lessons of World War II identified rapid damage repair and return to service as critical capabilities that require dedicated resources and specialized training rather than being treated as secondary support functions. The welding approaches pioneered by Canadian maintenance crews became foundations for contemporary armor repair procedures, with the multi-pass technique and thermal management principles now standard practice taught in military welding programs worldwide. The transformation from dismissed cheap trick to recognized innovation validated the importance of practical expertise and demonstrated that significant military advantages could emerge from unglamorous technical work performed by skilled craftsmen far from the spotlight of heroic combat narratives. The final accounting of how Canadian welding innovation contributed to Allied victory must consider both the measurable tactical advantages and the broader implications for understanding military effectiveness and technological development during wartime. The direct impact can be quantified through maintenance statistics showing that Canadian armored units maintained operational readiness rates 10 to 15% higher than comparable Allied formations, a difference that translated to dozens of additional tanks available for combat operations at any given time. Over the course of the Northwest Europe campaign from June 1944 to May 1945, this sustained advantage meant that Canadian armored divisions fielded the equivalent of an extra regiment's worth of tanks compared to what would have been available using conventional maintenance approaches. This additional combat power contributed directly to the success of operations, from Normandy through the final defeat of Germany, enabling sustained offensive pressure that German forces could not match or counter effectively. The human cost of armored warfare was reduced significantly by welding techniques that enabled faster repair and return of damaged vehicles, as tanks that could be quickly repaired and returned to service did not need to be replaced with new vehicles crewed by inexperienced personnel. Veteran tank crews whose vehicles were repairable could return to combat in familiar tanks rather than being reassigned to replacement vehicles, maintaining unit cohesion and preserving the tactical expertise that came from combat experience. This continuity of experienced crews multiplied the effectiveness of Canadian armored units beyond what raw numbers of available tanks would suggest, as veteran crews were far more likely to survive engagements and achieve objectives than replacement crews still learning how to work together effectively. The welders who kept these tanks operational were thus directly contributing to saving the lives of tank crews who might otherwise have died in new vehicles with unfamiliar crews. The broader lessons about innovation and military effectiveness that emerge from the Canadian welding story challenge conventional assumptions about how technological advantages developed during wartime. The innovation came not from formal research programs or government laboratories, but from practical problem-solving by skilled craftsmen facing immediate operational challenges. The development process was empirical rather than theoretical, with techniques refined through trial and error rather than systematic experimentation guided by scientific principles. Academic engineers dismissed the approach as crude and improper, even as it was producing superior results in practice, demonstrating the limitations of expertise that relies on theoretical knowledge without practical validation. The Canadian welders succeeded because they focused on what worked, rather than what theory predicted should work, remaining open to approaches that violated conventional wisdom, but delivered results under actual operating conditions. The transformation of Canadian welding from object of German mockery to recognized strategic advantage mirrors the broader pattern of Canadian military contributions during World War II, as forces initially dismissed as colonial and second-rate proved themselves through demonstrated competence and innovation that exceeded expectations. The cheap welding trick became a source of pride for Canadian veterans, who recognized that their nation's contributions to victory extended beyond combat heroics, to include technical innovation that multiplied Allied effectiveness. Modern Canadian military identity continues to emphasize this combination of practical problem-solving and technical competence, maintaining the tradition established by the welders and mechanics who revolutionized armor maintenance under the pressure of operational necessity. The legacy of their work endures in contemporary military maintenance doctrine and in the broader recognition that innovation can emerge from unexpected sources when skilled personnel are empowered to solve problems creatively. In the final analysis, the story of how Canada's cheap welding trick made Allied tanks virtually indestructible reveals fundamental truths about warfare and innovation that transcend the specific technical details of armor repair procedures. Victory in sustained military campaigns depends not just on the quality of weapons and the courage of combat forces, but on the unglamorous support functions that keep equipment operational and forces supplied. Technical innovation does not require sophisticated laboratories or academic credentials, but rather demands practical expertise, creative problem-solving, and willingness to challenge established practices when they prove inadequate. The German officers who mocked Canadian welding as crude and desperate improvisation failed to recognize that effectiveness matters more than conformity to theoretical standards, learning too late that their dismissive assumptions about colonial capabilities had blinded them to a significant Allied advantage. The welders who developed these techniques deserve recognition not just for their technical contribution, but for embodying the practical competence and innovative spirit that characterized Canadian military service throughout the war, proving that great nations are built not just through heroic sacrifice, but through the skilled work of craftsmen who solve difficult problems under impossible conditions.